No. I'm going to put you on the spot here. If I think about a perfect gas and I have, and I'm at STP, we know something about 1 mole of any gas. Doesn't matter what gas it is. It could be hydrogen, helium, whatever. There's something that we know about the volume of 1 mole of gas at STP. I'm going to throw it open to any of you guys. Do any of you remember how many liters that is? I heard it, but I just didn't hear it real clearly.
22.4.
Perfect. And this is a biggie, all right? And this is going to be what allows us to do what I'm getting ready to do. All right, so we already know, and if we go back and think about the combined gas law, right? So the combined gas law, we said, was when we have a pressure and a volume and a number of moles and a temperature, that number, when I do all of that, is going to be equal to the pressure and the volume over the number of moles and the temperature at the end, because at the end of the day, these things are constant. And if I'm constant, that means that I don't change, okay? So the combined gas law was really good when we had sort of two separate sets of information, two separate, and I think I misspelled separate there, two separate sets of information. And what do I mean by that? I mean, I know the pressure and the volume at the beginning, and I know the pressure and I want to find the volume at the end. There was always a beginning and the end, first and second. Now what we're going to do is we're going to say, well, wait a second. If this formula, PV over NT, is constant, then there must be a number that that's equal to. And where that number comes from right up here, because look at this. If I talk about standard temperature, I'm going to come over there to you, Nate Gerke. Standard temperature, that's a temperature of what, sir? What is standard temperature? And it's okay not to remember.
I don't remember it.
Okay. Does anybody on the call remember what standard temperature is? It's 0 degrees Celsius. Now for gas law problems, we never work in Celsius. So we're going to go ahead and just convert that right over to Kelvin. So if I'm talking about standard temperature, I know the temperature, it's 273 Kelvin. Now, hopefully you haven't forgotten what standard pressure is. How much pressure do we feel right now pushing down on us? How many atmospheres?
1.
Beautiful. Beautiful. So I'm going to go ahead and say that I know that the temperature is 273 Kelvin. The pressure is 1 atmosphere. And so we also know that for 1 mole of gas, and that's what N is, 1 mole of gas, we know the volume. So if you look at this, I know, and I know I'm a little bit off the screen there, so let me scooch up. I've got my P, I've got my V, I've got my N, and I've got my T. So if I wanted to know what this constant was, all I have to do is plug it in. All right, so I'm going to go ahead and do that. I'm going to scooch this down and over so I've got a little more space. So if my pressure is 1 atmosphere and my volume is 22.4 liters, that's the P and the V, and then that's over N times T. N is 1 mole. And then the temperature is 273 Kelvin. All I have to do is throw that into a calculator. And when I throw that into a calculator, and you don't have to necessarily have a calculator out and handy, right? This is going to give you 0.0821. And then the units for this, they're kind of crazy, all right? And don't worry about it, but I'm just going to put them on here. So up top, you've got liters times atmospheres. So that's liter atmospheres. over in the bottom, you've got moles times Kelvin. So it's a liter atmosphere per mole Kelvin. And so at this point, you're like, oh, what am I going to do with this? Well, this is a constant, and constants never change. So this is going to be an important number here as we get ready to come up with this, what we call the ideal gas law. Now, a couple days ago, and I'll pause for just a second. Any questions up to this point? Just doing a little bit of math. Okay. So a couple days ago, we talked about the fact that one atmosphere, there are different units for pressure. Another equivalent unit is kilopascals. And we also know that we can do this in millimeters of mercury, which is the same as torr. And for some people, like, don't sweat that. It's not a big deal. They're just different. It's like saying 1 foot is 12 inches. Okay, they're just different ways of talking about the same thing. A dozen is equal to 12 anythings. So what we're going to do is we're going to come up with this constant, but we're going to do it for the 3 different pressure units I have. So we've already done it for atmospheres. Right? Now we're going to do it for kilopascals. So I'm going to just show you that one. So I'm going to do, again, a temperature, a pressure, an N, and a V. So instead of doing 1 atmosphere, I'm going to do 101.3 kilopascals. I'm going to do 22.4 liters. I'm going to divide it by 1 mole. And I'm going to do 273 Kelvin. All right. And if I throw that one in the calculator, I want to just double check to make sure that I didn't write this down wrong. It's been a little while. Mr. Caldwell still needs to get more coffee in him here. So 101.3 times 22.4 divided by 273 is 8.31, and that's liter kilopascals per mole Kelvin. So now we've got 2 constants, all right, because we have 2 different units for pressure. This one is the unit for pressure with atmospheres. This is the unit for pressure with kilopascals. And then we just do the other one, which is 760 millimeters of mercury. So I'm going to do my pressure, 760 millimeters of mercury times 22.4 liters. Again, that's what the volume is for 1 mole of gas at 273 Kelvin. And so we throw that in our calculator, 760 times 22.4, and we get 62.4. And then that's liters. And then remember, we can use these interchangeably, millimeters of mercury or torr, same, mole Kelvin. And at this point, you're like, okay, not sure what I'm going to do with this stuff. All right, so now let's kind of put this all together. So we came up with 3 constants. These values are what we call the ideal gas law constants. And where do these come in handy? We know that PV over NT is equal to some constant. And so we're going to give that constant a letter. Chemists decided that they were going to use the letter R. And so R is the ideal gas law constant. And you're like, well, wait a second. How can something be constant if there are 3 different values? Which one you're going to use? The 0.0821, the 8.31, or the 62.4 is going to depend on the pressure unit that you have in your problem. If you have a pressure in atmospheres, you're going to use this one. If you have a pressure in kilopascals, you're going to use this one. And if you have a pressure in millimeters of mercury, you're going to use this one. So now we're going to take this guy and just rearrange it into what I affectionately call Pivnert. I'm going to multiply the N and the T over. And so this is typically what we refer to as the ideal gas law. All right. And so this guy is super valuable, all right? And we can do some problem solving with it. And the thing that you'll notice with this one, there's no initial and final. There's no one set of data and no second set of data. It is just, if you have some of these variables, you can probably figure it out for the rest of the variables, all right? So let me jump into a example problem. Let me close this. Does anyone still need the screen shared? I'm gonna change over here. Okay, so let me go ahead and stop sharing there. All right, have I completely bored you? The answer is yes. Lauren, Stella, and Chris, any questions so far?
I'm good.
No, I'm fine.
Okay, all right, so let's get this all kind of wrapped up here in a nice, neat little package and send you on your way for the day. All right, so let's see here. Okay. Lauren, can you give me a heads up saying that, yeah, we see your screen, it says ideal gas law, partial pressures.
Yeah.
Okay, cool stuff. So let's go ahead and zoom down here real fast to an example problem. These are the notes that are in your in the Canvas module for today. And so if I look at the formula, all right, PV equals nRT, what you're going to be looking at is I'm going to give you some information. So I'm just showing you this and I'm going to write this stuff down so we can work it out together. So if I wanted to determine the temperature, all right, so I want to find T, all right, and I want to do it in Celsius. And it tells me that I've got a number of moles of 2.49 moles. It's in a volume of 2 liters and it's at a pressure of 143 kilopascals. That's the question that I want to look at. So the first thing that I'm going to do, I'm going to pop over here back to this guy, is I'm going to now just, hey, let's just do some math. This isn't super scary. Come on, there we go. Sorry about the delay there. All right, so if we have this new formula, PV equals nRT, all right, you'll notice that it doesn't tell me the pressure at the beginning and the pressure at the end, the volume at the beginning, volume at the end. It just gives you one set of values. So the ideal gas law, joke coming here, is ideal if it's only one set of values. If you ever have two sets of values, you're going to want to use the combined gas law. But here, you're just going to say, okay, since we know that PV equals nRT, I'm going to go ahead and say, well, the P is 143, so we know this. We know the volume is 2. We know the number of moles is here, and we're trying to solve for this. Now, I'm going to come to you guys with a question, all right? I've got 3 different R values. I've got an R value of 0.0821. I've got an R value of 8.31, and I've got an R value of 62.4. Nate Gerke, which R value should I use here for this problem? Nate, you might be having some sound issues. I saw you pop out there. Chris, for this particular problem, which of these R values should I use? Did I lose everybody?
I'm here.
Lauren, you're here. Lauren, which R value should I use?
The 8.31.
Because that's the one that has kilopascals in it, okay? So what we're gonna do is we're gonna say, look, whatever the pressure unit is, that's what tells you which R value to use. So I'm gonna use an R value of 8.31 liter kilopascals per mole Kelvin, and then we're off to the races because I know everything except for T. I'm going to go ahead and just rearrange algebra-wise. PV over NR equals T, and then I just plug in. So I have 143 kilopascals. I have a volume of 2 liters. I have a number of moles of 2.49 moles. And then I have an R value that is this crazy wackadoo 8.31 liter kilopascals per mole Kelvin. And before I throw that in the calculator and do the math, I just show you that the liters cancels out, the kilopascals cancels out, the moles cancel out, and what I'm left with is Kelvin, but that's in the denominator of a denominator, so it flips. So if you throw that all into your calculator, you're going to get an answer. And then I'm gonna go ahead and wrap this thing up. You guys have been super awesome and patient here with all the technical glitches, and can't find my calculator. All right, so 143 times 2 divided by 2.49 divided by 8.31, and unless I've done this wrong, the temperature is 13.8 Kelvin. And if I have a Celsius and I want to turn it to Kelvin, I add 273. So if I have Kelvin and I want to go to Celsius, I subtract 273. And I don't think, is this the right number? I want to double check that. 143.
That's what I got.
That's what you got? Okay.
Yeah.
It just looked weird and small and okay. So then 13.8 minus 273. I'm looking at a wicked cold negative 259 degrees Celsius. All right. And so this is the beginnings of sort of our practice and our work with this particular ideal gas law. So we need to wrap this thing up. I'm going to go ahead and stop the recording.